Hello everyone, my name is Saumy and I welcome you all in this TEQIP GATE classes initiative. So this is my 10th lecture of the subject material science. So in this lecture, I will discuss more about the crystal defects. Okay, so let's crack the gate. So what are the imperfections in the crystals and why they exist in a crystal? Let's see. So in reality, perfect crystals do not exist. There will be some kind of imperfections always. Okay, and these imperfections or defects, they may affect their physical and mechanical properties. Okay, so like because of presence of these imperfections or defects, there will be change in the mechanical properties, like you can say yield stress or ductility. Okay, and other physical properties like you can say conductivity. It affects your conductivity properties, or it affects the magnetic related properties. Okay, so what is crystalline defect? So it is the lattice irregularity or the imperfection in the regular geometric arrangement of the atoms in a crystalline solid. ठीक है, मतलब आपका जो रेगुलर ज्योमेट्रिक अरेंजमेंट था किसी भी क्रिस्टल लैटिस में एटम्स का, ओके, तो वो अगर उस रेगुलर ज्योमेट्री से हट के कुछ रैंडमली अरेंजमेंट आ जाए कहीं कहीं पर, ओके, so that kind of things is known as defects in a crystalline solid or simply crystalline defects. Okay, तो यूजुअली इनके होने के अपने दो तीन कारण होते हैं. ठीक है, कॉज बिहाइंड दीज काइंड ऑफ क्रिस्टलाइन डिफेक्ट्स. ओके, सो वन मे बी ड्यू टू, बोल सकते हैं सॉलिडिफिकेशन, ड्यूरिंग सॉलिडिफिकेशन, नॉट ड्यूरिंग सॉलिडिफिकेशन. ओके, सो लाइक सॉलिडिफिकेशन में आपने पढ़ा भी है इन कास्टिंग. सो लाइक इफ देयर इज अ डिफेक्ट in solidification, so there may arise some sort of problem. Okay, so यहाँ पर भी आपका ये मॉलिक्यूलर लेवल में होता है, वहां पे आप ऐसा बल्क केस में देखते हैं ना, आप जो नेकेड आई से मैक्रोस्कोपिक स्केल में देखते हैं, यहाँ पे क्या होता है एटॉमिक लेवल में क्या हो रहा है कि ड्यूरिंग सॉलिडिफिकेशन आपने जो टेम्परेचर रेट है उसको ढंग से कंट्रोल नहीं किया है, जिसकी वजह से वहां पे जो मॉलिक्यूल्स है या फिर जो एटम्स है जो उनको रेगुलर स्पेसिस में बैठने चाहिए लैटिस पे, वहां पे उस तरह से वो सिट नहीं करते. ओके, so it may be during solidification due to rapid cooling and all. Okay, and second it may be due to like radiation. Okay, so radiation मतलब ये ऐसा होता है ना, radiation usually have very high energy. Okay, so because these x-rays or neutron rays, okay, so when they penetrate or when they obstruct or when they strike the material or some metallic object, so what happens, they have very good amount of energy, or you can say very high amount of energy. So this energy is being provided to the atoms who are sitting quietly in their lattice points. Okay, सो ये जो एनर्जी, अब इनको इतनी ज्यादा एनर्जी मिल जाती है उस एटम्स को वहां पर उस लैटिस पर्टिकुलर पॉइंट पे, एटम्स की बात करें या एनायन कैटायंस की बात करें, तो उनको वो एनर्जी मिल जाती है ड्यू टू दिस रेडिएशन कि दे ट्राई टू जंप आउट ऑफ देयर रेगुलर lattice and they will like sit between either in the some voids or they may occupy some another lattice point. Okay, so since this radiation provide them enough energy, so they jump from their regular lattice point and they will sit at some another point, either maybe in between the two lattice points within the some void. Okay, or either they may replace some another lattice atom. Okay, so this may happen due to radiation. Okay, so the crystalline defects, these are classified as point defects or zero-dimensional defects. Then we have line defects or one-dimensional defects. Then we have surface defects or two-dimensional defects, and volume defects, which is three-dimensional defects. Okay. So in this lecture, we will discussing mainly your point defects or zero-dimension defects. Okay. So what are the point defects? So these are the defects due to imperfect packing of the atoms during crystallization. Okay, तो यहाँ पे बात हो रहा है कि अगर आपका डिफेक्ट्स आ जाएगा बिकॉज ऑफ इरेगुलर पैकिंग ऑफ द एटम, मतलब एटम अपने रेगुलर प्लेस से निकल के किसी और प्लेस पर आपको वो मिल जाए, तो उसको बोलेंगे आप पॉइंट डिफेक्ट्स. ओके, पॉइंट डिफेक्ट और यू कैन से जीरो डायमेंशनल defects. Okay, so here atoms are missing or they are in the regular places in the lattice, in the irregular places in the lattice. Okay, so like अब हर क्रिस्टल स्ट्रक्चर का एक पर्टिकुलर आपको लैटिस डिफाइंड है, अब उस लैटिस पे वो आपका एटम अगर नहीं मिल रहा है तो मतलब क्या हो रहा है, आपका पॉइंट डिफेक्ट में आ जाएगा. ओके, so what are the different point defects? So first we have vacancy defect, then we have interstitial, then substitutional, and we have two special kind of defects known as Frankel defect and Schottky defect, mainly find in the ionic solids. Okay, so in the point defects, we'll see first is the vacancy defect. So from this diagram, you can see that this is a whole lattice, okay, and the lattice points are filled with the atoms, and you can see there is one atom missing over this point. Okay, so you can say whenever some atom is missing from their regular lattice point, so this kind of defect may be termed as vacancy defect. Okay, let's read this point. So in this type of defect, one or more atoms are missing from a normally occupied position. Okay, so these defects okay arise due to the vibrations of the atoms at high temperature. Okay, तो ये आपके क्यों यहाँ से निकल जाते हैं? Because again these atoms sitting at this regular lattice point, they are being given some energy, and this energy is due to your you can say temperature or thermal energy. Okay, and they take this energy and they vibrate, and they may jump out from their regular lattice point. Okay, so let's find what is the equilibrium number of vacancies due to the thermal vibrations. Okay, so this is given by the formula. So this NV, this is your number of vacant sites. Okay, so this is given as N into exponential of minus QV by KT. So where this N, this is your total number of atomic sites. Okay, so like for the given quantity of the material, N is going to be the number of the atomic sites. Okay, and this QV, this is your energy required for the formation of the vacancy. So it may have unit electron volt, or it may have a unit joules. Okay, so in this case, this is your Boltzmann constant. So and its value, it depends on which is the unit of your QV. Okay, so if QV it is given in joules, so K, this Boltzmann constant, this becomes 1.38 into 10 to the power minus 23 joule per atom Kelvin. Okay, and if it is given in if this QV value it is given in electron volts, so this K, this is going to be like 8.62 into 10 to the power minus 5 electron volt per atom Kelvin. Okay, so please remember these two values of Boltzmann constant. Okay, so because all the examiners, they expect students to remember the values of the physical constants like Boltzmann constant, Avogadro number, etc. Okay, so आपको ये याद रखना पड़ेगा ये values. This may not be given in questions. Okay, and this T, this is your nothing but temperature in kelvins. Okay, remember this is temperature in kelvins. Now this value of this N, which is your number of atomic sites, this is also given by a formula. This is given as Na into rho divided by capital A. Okay, so this is your Avogadro's number Na. This is density rho. Okay, this is given in gram per cc. Okay, this is density, and this is atomic weight given by gram per mole. Okay, and what is the value of Avogadro's number? This is equals to 6.023 into 10 to the power 23. Okay, 10 to the power 23 and atoms per mole. Okay, atoms per mole. Okay, so let's see this question. Okay, this is a practice question to understand the above formula. Okay, so calculate the equilibrium number of vacancies per cubic meter for the copper at 1000 degrees Celsius. Please read this question properly and take out your calculators and try solving this question. So the energy for the vacancy formation is 0.9 electron volt per atom. Okay, so it is given in electron volts. Okay, energy. So for one atom, you will require like 0.19 electron volts. Okay, so and the atomic weight and the density at given temperature is 63.5 gram per mole and 8.4 gram per cc. So let's see what you have to find. So take your time to solve it. So while I'm solving it here, okay, take out your notebooks, start solving the question. So read properly and see what is all given. So I think QV first and foremost work that you have to do is to write the formula. Okay, तो सबसे पहले formula लिखते हैं. So आपको क्या निकालना है? Equilibrium number of vacancy निकालना है, NV निकालना है. तो फॉर्मूला क्या है, NV इक्वल्स टू N एक्सपोनेंशियल माइनस QV by KT. Okay, this is the formula. Okay, and where N, it is given as Avogadro's number into density divided by atomic weight. Now you have to find this value, and let's begin with finding N, and then we'll proceed with different steps then. So let's see what is the value of N. Okay, so N, for N, atomic weight, density, all is given. Okay, so just find the value of N. So for N, like we have N equals to, this is Avogadro's number, is 6.023 into 10 to the power 23. Okay, and density, and this is given as 8.4, and divided by, this is weight is 63.5. Now you are going to get your answer in cc if you keep this density in gram per cc. Okay, but you require, this is your number of atomic sites, so you require this in atoms, because you require this, where is the question, you require this in vacancies per meter cube. Okay, so overall, if we are using this 8.4 gram per cc, so you will get atoms per cc. Okay, centimeter cube, you will get your answer. In order to get your answer in atoms per meter cube, okay, or in the answer vacancies per meter cube, okay, so what you have to do, you have to convert this gram per cc into gram per meter cube. Okay, just convert it into this cc into this cc, atoms per cc into atoms per meter cube. Okay, so like 1 centimeter equals to 10 to the power minus 2 meter. Okay, so 1 centimeter cube, this is going to be 10 to the power minus 6 meter cube. Okay, so just yeah, we will multiply over here, this is gram per cc. Okay, so this is gram per cc, a centimeter cube over here. So like this has to be multiplied with 10 to the power minus 6 over here. Okay, so like how it will be, so it will be into 10 to the power minus 6. Now this will be in atoms per meter cube. Okay, atoms per meter cube. So just find the value, calculate this value. Okay, how much it is coming, the value of N. Okay, so 6.023 into 20 power 23 into 8.4 divided by 63.5 into 20 power minus 6. Okay, so this is going to be, I will just writing the answer over here. So 7.96 into 10 to the power 28 atoms per meter cube. Okay, I hope you are getting the same answer. This is the answer of N. Okay, so from N you have to find the value of NV. So just put the value of N over here in this formula, and QV, this is given to as 0.9 electron volt. Okay, 0.9 electron volt, and T is 1000 degrees Celsius, so you have to use, okay, I'm just clearing everything else now. Okay, so this N, this is equals to 7.96 into 10 to the power 28 exponential minus, now this is 0.9 electron volt, and divided by, so this is K, this is Boltzmann constant, so this has to be in electron volts, as this is in electron volt per atom. Okay, so this has to be also electron volt, so this will be 8.62 into 10 to the power minus 5. Okay, and this T, this is in kelvins, and answer is over here, this is given in degree Celsius, this, so plus just add 273, so 1273 kelvins. Okay, just solve this value, how much you will get. Okay, so just solve this value. So I'm just writing the answer, I hope you'll understand this one. Okay, so just solve this, put over a minus sign, take the exponential, and just multiply with this quantity, and you will get answer to be 2.18 into 10 to the power 25. So the unit will be vacancies per meter cube. Okay, so this is your value of NV. So this is how you will find the equilibrium number of vacancies due to the vibration because of your thermal energy or thermal distortion. Okay. So now next is interstitial defect. So you can see from this diagram. So overall on this left we have a perfect crystal. Okay, so all the atoms are sitting on their lattice points. Now you can see this. This is your interstitial kinds of defect. You can see. So here in your regular lattice points. Okay, so within this lattice points there are some voids like this. Okay, there are voids. Different voids are present over here, and within this void if some foreign atom sits over here like from this you can see this yellowish or orangish this atom, it is nicely sitting up between these voids, in these voids. So you can see this kind of defect is known as your interstitial kind of defect, where some foreign atom it occupies the voids. Okay, please read this line. So these defects occur when an atom occupies the voids or an interstitial position without dislodging the parent atom. So over here, there is the foreign atom that is entering. It is not replacing any parent atom. It is just occupying the your voids position. Okay, or maybe interstitial voids. These voids usually known as interstitial voids. So they are occupying these voids. Okay, so how they are occupying, because the foreign particles their atoms is very small. Okay, the size of the atoms is very small, so they nicely sit within these voids. Okay, so and if the atoms is of same species as the lattice atoms, so it is called surf interstitial defect. Okay, so in case if the lattice atom is what it is sitting inside this voids. Okay, so that kind of defect is known as self interstitial. Like if you have a copper lattice over here. Okay, so and some copper atom it fills it comes inside and fill this void. Okay, so this kind of defect is known as self interstitial defect. Okay, and if some foreign particle is just entering into, so it will simply known as interstitial defect. Okay, next is substitutional defect. So from this diagram, you can see that this is your regular lattice shown by the blue atoms. Okay, and then we have some foreign element which is shown by this orange color. Okay, and this foreign atom, this is replacing the parent atom. Okay, and it is sitting nicely within this lattice. Okay, so what is happening over here? So when a foreign atom occupies the position of a parent atom or replaces the parent atom, then this kind of defect is known as substitutional kind of defect. Okay, so foreign atom is replacing the parent atom, and interstitial one, the foreign atom is just occupying the space within these voids. Okay, so if this kind of things is happening, then this is your interstitial defect. Okay, now we have two special type of point defects. So first one is the Frankel defect, usually happening in ionic solids. Okay, so what is happening in this? So whenever there is a missing atom which occupies the interstitial position, so that kind of defect is known as Frankel defect. Okay, so like what is happening, the atom it is getting some energy, okay, from some outside, and it is taking that energy and jumping from their its own regular lattice point, and it is just filling, and it is jumping from the regular lattice point, and it is going towards the some voids. Okay, so it is happening like this. So it is a combination of vacancy and interstitial defect. Okay, so like vacancy defect, what happens, that atom is missing from the regular lattice point. So similarly Frankel defect, what will happen, the atom will jump from the regular lattice point. Okay, in case of interstitial defect, what is happening, that some atom it is occupying the voids. Okay, so similarly, so that atom which is jumped from its regular lattice point, it will jump into the lattice voids. Okay, so it occurs usually in the ionic solids, as cations being the smaller in size is easily get placed in the voids. So we have anions and cations. Anions are usually bigger in size and cations are smaller in the size. Okay, so since cations are smaller in the size, so they may fit nicely within the voids. Okay, so from this image you can understand properly. So we have smaller cations and we have bigger anions. So similarly what is happening, you can see this the cation over here. Okay, so it has jumped from its regular lattice point and it has sit within this voids. Okay, so it is some void is some voids are left over here. Okay, so since there are some voids left, so what will happen, this cation will jump and it will sit within this voids. Okay, so this kind of defect is known as Frankel defect. So there is no change in, okay, electric charge, you can say electric charge, or no change in electronegativity. Okay, so there we have same number of cation anion before the defect and same number of cation anion after the defect has formed. Okay, so there is no change in electric charge or such electronegativity also. Okay, so coming to the Schottky defect, second type of special defects in the point defects. Okay, so now what is happening in this? So in this, the pair of positive and negative ions, or you can say cation and anion, is missing from the crystal. Okay, so this kind of defect is known as Schottky defect. तो मतलब पूरा एक पेयर, एक एनायन एक कैटायन, दोनों आपका लैटिस पॉइंट से आपका निकल जाता है. ठीक है, so it get moved out. Okay, so since for every anion vacancy there exists a cation vacancy, so the charge neutrality of the crystal is maintained. तो जैसे कि आपका फ्रैंकल डिफेक्ट में देखा था, वहां पे कुछ भी इलेक्ट्रिक चार्ज में कोई भी चेंजेस नहीं आ रहा था, तो सिमिलरली यहाँ पर भी आपका चार्ज जो न्यूट्रलिटी है इट इज कांस्टेंट. ओके, बिकॉज फॉर एवरी वन एनायन वैकेंसी देयर इज द वन कैटायन वैकेंसी. तो एक एनायन कैटायन दोनों एक साथ निकल रहा है, तो एक पॉजिटिव चार्ज निकल के गया बाहर, तो एक नेगेटिव चार्ज भी आपका बाहर निकल के जा रहा है. Okay, so with this diagram you please understand what is the Schottky defect. Okay, so like we have smaller cation and bigger anion. So this we have a defect. So in the Schottky defect, both cation is moving out of the lattice point. Okay, this is a cation, and the anion is also moving outside the lattice point. So you have a pair of a vacancy, a vacancy pair of anion and cation. So now what is the difference between the Frankel and Schottky defect? कोई बता पाएगा? If this is your diagram of Schottky defect and this is the diagram of a Frankel defect. Okay, so यहाँ Frankel defect में क्या हो रहा है, कैटायन आपका रेगुलर लैटिस पॉइंट से निकल के वॉइड्स में बैठ जा रहा है. Okay, इन केस ऑफ अ Schottky defect आपका कैटायन आउटसाइड द लैटिस चला गया है और आपका एनायन भी आउटसाइड द लैटिस चला गया है. Okay, तो सिमिलैरिटी तो यही है कि वहां पे इनमें कोई आपका चार्ज का कोई भी चेंजेस नहीं है, मतलब आपका इलेक्ट्रो चार्ज जो है दैट इज सेम बिफोर द डिफेक्ट एंड आफ्टर द डिफेक्ट. ओके, सो देयर इज नो चेंज इन द इलेक्ट्रोनेगेटिविटी. सो हाउ इट इज डिफरेंट? ओके, सो डिफरेंस इज ओवरऑल वी कैन से डेंसिटी. ओके, सो जो फ्रैंकल डिफेक्ट है वहां पे आपका जो कैटायन है वो निकल के लैटिस पॉइंट से बाहर नहीं गया, वो आपका सिर्फ वॉइड्स में ही रह गया, मतलब विद इन इट इज विद इन दैट ओन लैटिस स्पेस, है ना. तो लैटिस स्पेस के अंदर में ही, बाहर नहीं निकल के गया है. तो इसकी वजह से क्या होती है कि वहां पर जो आपके जो यूनिट सेल है या जो लैटिस है 2D लैटिस और 3D लैटिस, वहां पे कोई भी डेंसिटी का कोई चेंज नहीं है. ठीक है, बिकॉज we have same number of cation and same number of anion after the formation of the Frankel defect, so there is no change in the density. But in case of a Schottky defect, over here you can see that a pair of a cation anion is being removed from the lattice. Okay, from the lattice space, so you can say that due to this vacancy there is a decrease in the density. Okay, तो यहाँ पे क्या हो गया, आपका पूरा का पूरा वेकेंसी आ गया है एक कैटायन एनायन का, तो इसकी वजह से जो डेंसिटी है लैटिस में या क्रिस्टल स्पेस में वो आपका कम हो जाता है. ओके, सो in Frankel there is no change in the density. In Schottky we have a change in density, which means we get low density after this Schottky defect is formed. Okay, so this was all about the point defect in today's lecture. So in next class we'll talk about more about line defects and surface defect. So before wrapping up this lecture, let's see some practice questions. Okay, so this is IISc 2020. So please read the question. So if a pair of one cation and one anion is missing in an ionic crystal such that those pairs of ions are equal to maintain electrical neutrality, then that pair of vacant sites is known as, क्या है आपका, क्या है, एक कैटायन निकल गया एक एनायन निकल गया. ठीक है, पेयर निकल गया, मतलब यहाँ पे हो गया आपका ये Schottky imperfection. ओके, आंसर इज ए. फ्रैंकल में क्या होता है, आपका कैटायन निकल के वॉइड में चला जाता है. ठीक है, and the rest two, these are just some random options. Okay, so ESC 2020 is option A, and this is some practice question taken out from some workbook. Okay, then consider the following statements, find the correct ones using the codes below. Okay, so आपको ऐसा 3 स्टेटमेंट दिया है, देखना है इसमें से कितने सही हैं कितने गलत हैं. प्लीज रीड. So first is no change in the density of the solid in case of a Schottky defect, while the density decreases in case of Frankel defect. तो ये क्या लिखा है इसने, अपोजिट लिखा है. फ्रेंकल डिफेक्ट में कोई डेंसिटी चेंज नहीं होता है, शॉर्टकी में आपका डेंसिटी कम होता है. तो दिस इज वन इज रॉन्ग. ओके, so let's read second. So in Frankel defect, some of the ions of lattice occupy the interstitial sites, leaving the lattice vacant, है ना. तो यही होता है, कैटायन आपका रेगुलर लैटिस पॉइंट से निकल के इंटरस्टिशियल साइट्स या वॉइड्स पे चला जाता है. तो दिस इज करेक्ट. एंड लेट्स सी थर्ड पॉइंट. So Schottky defect occurs when equal number of cations and anions are missing from lattice. Okay, so this is also correct. So we have two statements correct, which is statement 2 and statement 3. So option is D. Okay, so this is a correct option. So this was all in today's lecture. I hope you have understood some basics of the point defects. Okay, so we'll meet in the next lecture. Till then, have a good day. Thank you.